Université de Littoral, and he will talk about a logical analysis of Banach's fixpoint.
Thank you, Mariana. It's a very good question. So I wonder a lot of questions because I'm coming out of session 1 with people by sleep and just before coffee break. Anyway. So indeed, this is a short note on joint work with a PhD student. And to start off, I'll take you back 100 years. So the 1920s, Stefan Banach was a Polish mathematician who wrote his PhD thesis on functional analysis. There are a few remarkable things about this thesis. It's written in French, which instead is still a scientific language. It was published at the University of Leopold, which today is called Lviv, and where there is war raging. But also he proved in his thesis what we call today Banach's fixpoint theorem, and I present you here a modern version. So if you have a complete metric space and you consider contraction, so K contraction with a parameter K is strictly between 0 and 1, K liquids, then you pick any element X in your non-empty space, you start generating the sequence, the Picard iteration as it's sometimes called, and what Banach proves is that from contractivity he gets that the sequence is Cauchy. Because this space is complete, this sequence then converges. He again infers from the non-expansiveness of such a contraction that this limit point is actually a fixed point. And the second use of contractivity is that any two such fixed points are actually at distance 0 of each other and therefore equal. Right? So this is what we all learn at some point early on in our analysis courses or topology courses. Now, some 50 years after Banach comes another giant with a paper that was mentioned before in the Lauvier session, and I think also Dirk mentioned it yesterday. And Lauvier in 73 notably stated that it is possible to regard a metric space as a what we call strong category, what we call a rich category today. And moreover, by specializing constructions and theorems of general category theory, we can deduce a large part of the general metric space theory. And so this suggests that actually the Banach fixpoint theorem could perhaps hold for a category instead of a metric space. Now, luckily for us, Lauvier also proved or showed in that paper how we can think about Cauchy sequences and completeness and convergence. So my task today, what I want to explain to you today briefly, is that indeed there is a sensible notion of contraction from which we can still infer the very same theorem. Now, it's not all categories that I will, any general categories that I will be talking about. I will talk very specifically about quantile-enriched categories. So there are V categories where V is a posable monoidal category, small, co-complete, and closed. Right? So it means that it's a closed, or as the logicians would say, residuated, monoidal complete lattice, such as in particular co-limits, so suprema. And because of the adjoint functor theorem, because everything is small, closeness just means that multiplication distributes on both sides over suprema. Both sides because I don't want the monoidal structure to be symmetric. Because it's simply not necessary for the result. Even though many examples are symmetric. Right, so just keep in mind the enriched category theory, as Steve was mentioning, and repeat all your definitions, acknowledging that because the V is settled, about all coherence issues disappear. So things become a lot simpler. In particular, a Q category A is just a Hom function with a transitivity and a reflexivity axiom, so composition and units, no coherence required. A Q functor between such Q categories is a mapping on objects that is functorial in a sensible way. And there is always, it takes three to tango, so there is also the notion of distributor that in some other talks have been replaced by maybe pre-sheaf constructions or maybe some sub-object notions, but you always do three things. And so a Q distributor, in the absence of symmetry of the monoidal structure, I define it as a matrix. So I think also Christina has been using this kind of idiom. So it's a matrix with, say, B rows and A columns that assigns to every tuple Y, X an element in your base category Q, base quantile Q, such that you have this action on the left by B and on the right by A. Again, no coherence use, everything is falsetto. And it's precisely as you would do for the enriched categories, D functors and D distributors. You get a category cat Q in the obvious way of categories and functors. You get a super-enriched two-category dist Q of Q categories and Q distributors. And in the second one, so it's maybe a little less familiar, but you compose with a matrix-like formula, and local order is given element-wise. So these notations, these notions are very well known, and it's actually a perfect occasion to bring up another giant category here, another very colorful figure. So Jean Banach defined these distributors, and I call them distributors because of Ryan Louvain. These famous notes on distributors were written after a course, a master's course here in Louvain. And the author of the notes, which were approved by Jean Banach, is Jean. So it's one of those famous papers of Banach that were written by students of Banach. So, and you can see that in these notes, which are absolutely wonderful, and I invite you to look them up, he uses the same notation, the same contra and covariance, so I'm using these conventions. Right, so a couple of examples. The ones that Lovir discussed in his paper are ordered sets, where you take your base quantile to be 0, 1, just Boolean algebra, and metric spaces, where you take what we sometimes call the Lovir real, so positive real numbers with infinity, but you look at it upside down. So your top element of your lattice is 0, and your bottom element is infinite, so it's the opposite of the natural order, and your nodal structure is plus. So the hom in the first case is just the characteristic function of the order. The hom in the second case is the distance. Right, now we can generalize this latter example, and it's done in what's sometimes called, it's a misnomer in my opinion, so fuzzy logic. So what people call in that case a left continuous T-norm is just a commutative integral meaning unit element is top element, commutative integral quantile structure on the unit interval. That's what people call a left continuous T-norm, precisely the same thing. It's used in many-valued logic, which I find a better name for fuzzy logic, and when you enrich over this quantile, you get what people sometimes call fuzzy order and fuzzy monotone map. Now, for very general reasons, because soup a symmetric monoidal closed category, if you look at two commutative monoids in soup, you can always compute their co-product in the category of commutative monoids in soup. Turns out that this co-product is computed with tensors, underlying tensors, and because soup is star autonomous, a tensor product in soup can also be described as a hom object. And it explains the last example. You can compute the co-product as commutative monoids in soup of the two previous examples. So a left continuous T-norm and the metric example. If you compute all this, you have this tensor product of these complete lattices, and its elements are actually what people call probability distributions. They are precisely, say, lower semi-continuous functions from 0 infinity to 0, 1. And the product which is present in this quantile, and this co-product of this quantile, is a convolution product. Now, if you enrich over this quantile, then you obtain what people have been calling Menger spaces or probabilistic metric spaces. So here the hom of the enrichment is computing the probability that the distance from x to y is less than t. So it's another batch of interesting examples, and there are many more examples where actually the quantile is not commutative, for example in sheaf theory or non-commutative topology, monoidal topology, and so on and so forth. Okay, so crucially, any Q functor between two Z categories or Q categories represents a left adjoint distributor, the graph of the functor. But not every left adjoint distributor is thusly representable. But when it is, it's uniquely so, and so this merits a name. And I think it was after Robert himself that people now call this a Cauchy complete category. It's one such that every incoming left adjoint distributor is representable. So here's a very particular case. If you take a sequence of objects in a Q category C, then it determines a pair of distributors which goes from the one element category into C. So there's a distributor phi defined by this sup-inf formula, somehow measures distance from a point y to the points of this sequence. And there's another one, sort of with the hom in the other way around, which is called psi. And so these are genuine Q distributors between these two categories. And it turns out that phi is left adjunct to psi if and only if you have this sup-inf formula going on. So the sup-inf of this C, x, and xm should be bigger than 1 being the monoidal unit in Q. Now if you apply this formula to the metric case, remembering that you have to put everything upside down and that your unit 1 is actually the number 0 and that product is actually sum, then you end up with a limit formula which is precisely saying that the sequence is Cauchy. So in general, I'll just take this as a definition. I'll say that the sequence is Cauchy if phi is left adjoint, this particular phi is left adjoint to psi. Now this left adjoint distributor is then furthermore representable, so by a functor which goes from 1 to C, which therefore just picks out an element called x star, if and only if, I'm just writing. Once more, if I apply this formula to the metric case, you end up with a limit formula precisely saying that the sequence is convergent in the metric sense. So, in a Cauchy complete category C, all Cauchy sequences converge. Now, in fact, this categorical Cauchy completeness, so representability of left adjoint distributors, is a bit stronger than sequential Cauchy completeness. And under certain conditions on the Q, these both notions coincide, notably in the metric case. And there's a nice paper by Hoffman and Reis from 2013 where the analysis is carried out. Okay, so now I can move on to the fixed point theorem. Suppose that I have a Q functor, F, and no functor on C. C is Cauchy complete. I'm just copying the conditions in the classical fixed point theorem. And for my first proposition, I will immediately suppose that iterating x, fx, ffx, and so forth produces a Cauchy sequence. Suppose it does. Then actually f has a fixed point. Right? So why? Well, because if I'm assuming that f and x is a Cauchy sequence, then I have this adjoint pair of distributors. The left adjoint one is representable because this is, the convergence that I assume is possible in this category, which I assume to be Cauchy complete. And a small computation, just using functoriality, shows that, well, if you compute the hom between fx star and x star being this convergence point of this hypothetical Cauchy sequence, then actually the hom is above, you compare C fx star x star with C x star, precisely as in the metric case. You just copy the metric argument. You end up with a hom which is bigger than 1. Now, bigger than 1, use your V-enriched yoga. It means that there is an isomorphism between x star and x star, so also between fx star and x star. And if you do the same computation with psi, you also find that the hom x star fx star is bigger than 1, meaning that there is actually an isomorphism in the sense of an enriched category. Right, but of course, I didn't use contractivity, and I assumed that there was a Cauchy sequence by p-type iteration. But the point is, therefore, can we provide contractivity conditions on F to ensure the existence of a Cauchy sequence, to make this a Cauchy sequence? And can we say something about, perhaps, the uniqueness of such a fixed point? So we need to introduce the notion of contractivity, and this is what we came up with. So this is what I propose. Somehow contractivity of a functor means that on top of functoriality, you have to be able to squeeze the functoriality in equation. You have to control it. You have to make it more and stronger than just being functorial. This is what this condition with the K in K-Lipschitz map is doing for Banach. And this is what I will imitate with a phi, little phi, from Q to Q. So I will call it the control function. So think of it as the scalar K of Banach. It's a control function. And I will say that F is a phi contraction if, well, this little phi is what Paul called inflationary, so phi of t is bigger than t. for all elements in Q. And it can only be fixed by phi. So there is a fixed point sort of condition built in this control function. It can only be fixed by phi if it's either 0 or bigger than 1. Right? And then this phi measures the contractivity of f, is expressed by the third condition. C of fx of y is bigger than, it would have been bigger than cxy by functoriality, but I make it strong functor, so contractive functor, by putting a phi in front. Okay, so how does this relate to the classical Banach case? Well, in the Banach case, again, everything is upside down. 0 is my monoidal unit, and plus is my multiplication, and suits become ints, order is turned around. So in the Banach case, it's actually phi which maps a real number t to k times t. And it's precisely such a control function. You can easily verify that there's different clauses, and being contractive in the metric case is precisely being a Banach contraction with a constant k. But, of course, the point is that there are non-trivial examples of such phi contractions also over other quantiles, and notably, you didn't find a whole, well, there are still a lot of difficult computations that we're trying to carry out, but there is at least one for these probabilistic metric spaces. So there are non-trivial examples for example, probabilistic metric spaces. Okay, so note that the phi contraction is always a Q functor. It's a sort of stronger functoriality condition that we have. So the previous proposition applies. When the Picard iterate is Cauchy, then it converges to a fixed point. So suppose now that you have two fixed points. So I claim that this notion of contractivity quite easily produces uniqueness of fixed points. So suppose that you have two fixed points, then again there is a little computation that you can do. You compute the hom between x star and y star, these two fixed points. They're equal to c fx star, fy star, because they are fixed points. This by contractivity is bigger than phi of c x star y star, which is bigger because phi is inflationary, bigger than c x star y star. So if you have it means that c x star y star is a fixed point of phi. So when I now refer to my fixed point conditions in little phi, it means that this hom is either 0 or bigger than 1. It's part of my conditions on phi. Now, permuting x star and y star, this leaves only four possibilities. Either both homs are 0, one is bigger than 1, the other is 0, the other way around, or both are bigger than 1. Right? What this actually means is that whenever your category is symmetric, which is the case, for example, for an ordinary metric space, as viewed as categories that are symmetric, when the category is symmetric, then any two fixed points of a phi contraction are either isomorphic, it's the right-hand possibility, where both homs are above 1, or both homs are 0. What this means is that they are in different summations of the category. Right? And if you have a category which has no 0 homs, this is also the case for a metric space, because there typically you would, in the classical case, you would say that distances are never infinite, which is the bottom element of the law of reals. So if C has no 0 homs, any two fixed points are always isomorphic, because the only possible case is the right-hand side. Okay. Now, so we have this convergence towards this fixed point. If the Picard iteration produces a Cauchy sequence, we have more or less uniqueness. We have analyzed this. Still should tell you if it is really the case that the Picard iteration produces a Cauchy sequence. And it does under certain conditions. So suppose that you have a phi contraction on the Q category. Suppose that Q is a continuous lattice. So meaning that it has directed supreme and commute with arbitrary infima. And suppose that phi is lower semi-continuous on the lattice underlying Q, so meaning that it preserves order and directed supreme. Then indeed, pick any element of your category, make sure that the hom between fx and x is not 0, and between x and fx is not 0. What this simply means is that x and fx cannot be in different summands. If you are in different summands, you cannot possibly converge to something. So take such an x, then indeed the sequence is Cauchy. Now, these conditions are met by the previously mentioned examples. I think it's obviously the case, you're all agreeing for a total order, so it's the case for the metric example. It's also the case for the fuzzy example. And in fact, because the tensor product of two continuous lattices is continuous, it's also true for the probabilistic metric spaces. In fact, the conditions, the result holds under slightly weaker conditions, but it makes a statement a little more involved, so I just skip it. Convenient. Okay, so this is the proof. It's probably too small to read, but I just show it because it's a manipulation of sups and ins in a clever way, right? And I'll try to give you an idea, a sketch of the proof. So it's done by contraposition. So if this Picard iterate is not Cauchy, it means that the Cauchy condition does not hold, and one is not below this sup-int. Because the lattice is supposed to be continuous, it means that there is an epsilon, it's sort of an epsilon argument, but in an algebraic way, not in an analytic way. There is an epsilon below 1, which is not below the sup-int. This means that there is this epsilon, which cannot be 0, because otherwise it would have been below. It cannot be 0, but it's still way below 1, such that, well, for all k, there exists mk, nk, such that this epsilon is not below such a Hom, right? And then comes the trick. There is a clever choice of indices far enough in the sequence that allow you to make a subsequence, which I've called dk. So I'm not at all explaining what happens. It's the core of the proof somehow. But you can make a clever subsequence, dk, so that using lower semi-continuity of phi, continuity of q, and the initial condition that fx and x are not at 0 distance, are at a non-zero, have a non-zero Hom. This sub-inf of these dks, of this subsequence, is actually a fixed point of phi. So again, I'm producing a fixed point on the quantile level. Now, being a fixed point, moreover being different from 0, means that via my conditions on phi contraction, this clever sub-inf should be above 1. Because the only fixed points of little phi are 0 and elements above 1. It's not 0, so it must be above 1. But I have my epsilon way below 1. 1 is a sup, a directed sup, moreover. So it says that epsilon is below such an inf for some n0, far enough in the sequence. But this is a contradiction because, in fact, epsilon is never below c fnkx fnkx. Right? So that's a very brief sketch of the proof. Right, so I can sum up and state a theorem. It says that suppose that f is a phi contraction of a Cauchy complete Q category. Suppose that Q is continuous as a lattice, and that phi is lower semi-continuous as a morphism, a lattice morphism. If there exists an x such that cfxx is not 0 and cxfx is not 0, then f has a fixed point obtained by Picard iteration. If C is symmetric, then any two fixed points are either isomorphic or in different summands, and if C has non-zero Homs, then any two fixed points are isomorphic. The examples, well, in ordered sets, everything trivializes, because part of the hypothesis then says that there is a fixed point. But if you carry out the theorem anyway, then you will notice that indeed this Picard iteration will go to the fixed point that you start with. For metric spaces, we find Banach's fixed point theorem with the Banach contraction, so with the phi of t equals k times t. And we find also a generalized version which was proved in the 60s by Boyd and Wong for non-linear contractions. If we look at the t, or the left continuous t norms, so quantile structures on the unit interval 0, 1, then we find a new fixed point for these fuzzy orders, but it seems to be related to known results, but not one-on-one. We still have to check this or look into this. And for probabilistic metric spaces, there are complete books on fixed point theorems for probabilistic metric spaces that I absolutely didn't know of before this work. It's by Hadzic and Papp in 2001. And we find a fixed point which is related to certain of their results, but again, it's not really clear how precisely their results would fit in or would suggest generalizations of what I presented. So the takeaway message, I think that the setup is quite easy. I am fully aware that the proof was too fast and cannot possibly be reconstructed this fast. But the takeaway message would be that actually, and this is sort of important for me, this is why I call it the logical analysis, is that there is an equilibrium of three things. So you need your category your Q category to be sufficiently co-complete, in our case, Cauchy complete. You need your morphism to be sufficiently contractive, and that's why I propose these 5 contractions. But for me, the surprise, perhaps, is that you need your quantile to be sufficiently continuous as well. You need algebraic conditions on the quantile Q for the whole proof to work. So our result captures known examples and produces some new results, but we still have to work a little to find more examples. But the real challenge, in my opinion, and that's why I insist on not having symmetry on the quantile, the real challenge would be to find such a fixed point theorem for quantaloid, so bi-category enriched categories, because I'd like to understand better the situation for partial metric spaces, which are metric spaces in which self-distance can be different from 0, and which are quantaloid enriched categories instead of quantile enriched categories. Okay, I think I'll stop with the reference. Thank you.
Questions or comments?
So, as I understand, one of the original motivations for quantiles was to have some constructed way of working with Isar algebras, as would be Mulvey, if I recall. And also, the Banach fixed point theorem, sort of classically stated, even the proof you gave at the beginning, is constructive. So it's kind of weird to me that the proof that you give for this fixed point theorem is non-constructive. Do you know, or relies on conviction? Do you know if there's a constructive version of this result? Is that something that you considered?
We tried and didn't find it.
Interesting. Thank you.
Sebastian?
On the fixed point is, you asked that the fixed point of phi must be either equal to 0 or bigger or equal to 1. That 1 is...
1 is not always the top element.
1 is the top element, so why not directly say equal to 1?
It's not always the top element.
Oh, okay.
Yeah, so that's not a requirement.
Okay, so in ordinary language, we say that a body contracts rather than a point or a sequence. Now, with numerical methods, if you use intervals instead of points and sequences, you can get some more reliable results for many purposes. And if given you've got these quantiles around, it just feels that it ought to be possible somehow to be talking about. I mean, what does it mean to be a contraction of a category? I don't know. Maybe that's needs to be thought about. So
you suggest to construct a quantile whose elements are interval, is that it? Or?
Something like that, or subcategories. I don't know. That sounds something new.
Sorry.
Thank you for the talk. It's a really nice problem and a very clear explanation. I was thinking that base change for enriched categories is playing an important role in the background here. When you multiply by k, that's a strong monoidal function from B to D, but of course you don't need a strong monoidal function to base change. You just use a lax one. That's equal to the whole world of LP spaces. So have you tried exploiting that point of view?
Yes, we have.
Base change for enriched categories?
Yes, we have, and so this phi actually, so in certain examples at least, this phi is a base change, and so this contraction is converted from C to phi of C, let's say. So maybe that's what the force is hitting at. The problem is that when we tried our hand at phi category in this case, the base changes preserve types. And for convergence, this is not necessarily what you want. So the problem somehow is that when you look at the quantaloid in this case, then it's as if convergence can only happen in a fiber over one of the objects of the quantaloid. And this is what we want to try to avoid. So we didn't find a technical solution, but your suggestion is definitely, I think it's even at the end of your statement, that's my point as well.
So there is the last question there, then we have the coffee break.
Thank you very much for this talk. It was really interesting. With you mentioned that the energy fixed points will be isomorphic. Is the isomorphism canonical by net? And if not, is that because it's out of our practice?
It's not because everything is possible. as in a pre-ordered set, if two elements in a pre-ordered set are isomorphic, they are in just one way. So that's the intuition that we're
Okay, let's second speaker.